All right, so we've looked at the pH scale and we've defined that an acid is below 7 and a base is above 7, and 7 is considered neutral. But what does the pH scale really mean? So the pH scale is actually the opposite log of the hydrogen ion concentration. So if you look at and you see brackets, that means concentration. So if you have a hydrogen ion concentration of 1 times 10 to the negative 4th, it means that the pH is 4 because of the exponent here, and it's acidic. Let's say you have a hydrogen ion concentration of 1 times 10 to the negative 5th. You have a 5 here, then the pH is 5. Now, if we compare these two, though, something that has a pH of 4 and a pH of 5, this is an exponential relationship. So something that has a pH of 5 actually is 10 times less concentrated than something that has a pH of 4. So let's look at an example where we have a concentration that doesn't start with a 1. And let me just show you how to punch this into your calculator. So I'm going to pull up the Almo really quick. And we're going to see that if you have a hydrochloric acid solution and this is the hydrogen ion concentration, what is the pH? So we just plug it into our calculator and we do the opposite log, and then you just punch in the concentration and hit enter. And we get 4.57 is the pH. So this is an acid. Now, if we want to then go in the other direction, so let's say we're trying to go from pH to hydrogen ion concentration. In that case, we take the pH and we make it the exponent and we make it negative. So again, if we look at the Almo, if we want to go in the opposite direction, I could say do 10 and raise it to the negative pH power. So negative 4.57. And I hit enter, and so I get the hydrogen ion concentration is 2.7 times 10 to the negative 5th. So that's how you go from hydrogen ions to pH and pH back to hydrogen ion concentration. Now, there's another more rare scale called the pOH scale that's not really used very often, but we're going to discuss it here, and it's looking at the hydroxide ion concentration. So it's similar to pH, but it is using hydroxide ions instead. So if we take the concentration of a hydrogen ion multiplied by the hydroxide ion concentration, we would get 1 times 10 to the negative 14th always. So let's say you're given a hydrogen ion concentration or hydroxide ion concentration, then you could just divide 1 times 10 to the negative 14th by one of these to get the either. Now, what this also means is that if we were to take the pOH of a substance and add the pH of the substance, we would get they would add to 14. Now, because of the pOH scale looking at hydroxide ions, the pOH scale is actually opposite of the pH scale. So acids are higher or greater than 7 on the pOH scale, and bases are lower than 7. So let's look at an example. So we have a potassium hydroxide solution, which is 4.6 times 10 to the negative 9th molar. What is the pOH and the pH? So I'm just going to pull up the Almo. The work is shown here, but I'm going to pull up the Almo so you can see how I punch it into the calculator. All right. So we're given the hydroxide ion concentration. So if we just use the opposite log, we can figure out what the pOH is. So 4.6, second EE to the negative 9th, and I get 8.33 is the pOH. Now, because pOH and pH add to 14, then we can just subtract this number from 14, and that gives us the pH of 5.66. And we know that it's acidic because its OH is greater than 7 and its pH is smaller than 7. All right, so when we look at pH indicators, we can use all different sorts of indicators in order to determine the pH of something without performing a calculation. So I'm going to discuss just a few of these indicators. pH is usually indicated by a color change. So if something's acidic or basic, it changes the color of a substance. So we have pH paper that we've used in the lab, which will change color based on its acidic or basic quality. And so typically you're going to moisten this paper by dipping it into a solution or dropping some acid or base on it, and you can compare it to a scale. Now, universal indicator works the same way. So universal indicator is a liquid that we would add to a solution to figure out what its pH is. And again, based on its color scale, we would compare it to you know, a graph or something that would show us what pH that color specifically indicated. So some of the limitations we see with these acid-base indicators, typically they're very temperature sensitive. They also don't work very well if we have a solution that has a specific color. And distinguishing color is a human ability that can be subjective, so if you're colorblind, that could be an issue as well. So really the best way to determine acids and bases is to use something called a pH meter. And a pH meter gives a more definitive result, and it actually uses the electrolyte quality of the acid or base to distinguish, to show the pH. Some problems with this is that usually they're large, they're difficult to move around. However, but they measure voltage using electrodes, so they can measure a very, very accurate and true pH, as opposed to the other scales where we're looking at like 2, 4, 6, and 8, and we know that that's an exponential difference. pH meters also need to be calibrated, and they need to be stored properly, and so there's a lot of maintenance that goes with dealing with a pH meter.